So the next layer that we're going to add is talking about the rotational version of Newton's second law. So Newton's second law up till now, as we've discussed it, basically says that the net force acting on an object is equal to mass times the acceleration. So this is a vector summation over here, and then that sum is going to be equal to mass times the acceleration vector. But really we want to think about this as the translational version of Newton's second law. Up until now, we've basically been able to treat every object we dealt with as if it were a point particle. And so what this particular equation has told us is that it's basically described the center of mass motion of a rigid object. So if you can act like your object is simply a point particle, then the only thing that's moving around is the center of mass. And that's the way we've treated everything, because our free body diagrams up until now, we've drawn everything as a single point. We said that this tells us that the vector sum of the forces acting on the object change how the center of mass of an object moves by causing acceleration. So you take the vector sum of all the forces, that's going to tell you how the object's motion is changing, because that will tell you whether or not you have an acceleration. It tells us that the net force and the acceleration always point in the same direction, because mass is always positive. And then the thing it tells us about mass is that mass is a measure of an object's resistance to being accelerated. So how the center of mass motion changes, right, basically depends on, well, if you've got something that's really massive, you're going to need a really big net force to get its center of mass motion to change much. So the bigger you make the mass, the more resistant to having its center of mass motion changed an object is. So what we're going to add now is basically the rotational version of Newton's second law. And again, notice what we've got. We've still got a vector equation. We've got the net torque, right? The vector sum of all the torques acting on the object is equal to I goes by two names. It gets called the moment of inertia. It gets called the rotational inertia. Those two things mean exactly the same thing. And so the net torque is going to be equal to the moment of inertia times the angular acceleration. So again, here you get a sense of, we talked before about what do we swap out when we go from translational problems to rotational problems. And you're seeing that we're going to swap forces for torques. We're going to swap moment of inertia for mass. And again, we already know that we're going to swap angular acceleration for acceleration. So what does this tell us? Well, again, what this tells us is it describes how a rigid object rotates about its center of mass. So our translational version tells us how the center of mass moves. This equation tells us how an object rotates about its center of mass. It tells us that the vector sum of the torques acting on an object change how an object rotates about its center of mass by causing an angular acceleration. It tells us that that net torque always points in the same direction as the angular acceleration. And so again, what we talked about in class yesterday was that we know that we can figure out the direction of the angular acceleration by thinking about whether our object is speeding up or slowing down as it rotates. We know that that direction is always going to point along the axis of rotation. Well, the net torque is also always going to point along the axis of rotation. And then this last term, the moment of inertia is a measure of an object's resistance to having its rotational motion change. So in exactly the same way that we talked about mass is a measure of an object's resistance to having its center of mass motion changed, the larger you make the rotational inertia, the larger the torque you need to change how an object is spinning. And so we'll put these things together in class in working rotational inertia problems tomorrow.